Yeah. So far we have, well, this description is rather abstract, yeah. So this, well, we have certain particular cases where we can calculate these Brauer groups, but so far we don't have any, well, some kind of general classes of fields. So of course we have just some general class of fields like separably closed, yeah. Then where this group is trivial, yeah. But otherwise we don't have many examples of concrete calculations. So let's consider the following case, which is also particular, but somewhat more general. So, so assume that maybe let's call it. Well, we fix some integer. Well, at least 2. So we consider we are looking for R-torsion in Brauer groups in Brauer group of K, assuming that this field contains a primitive rth root of unity. Contains a primitive root of unity. Yeah. So what we can do? So you see that this group, so this Brauer R-torsion group, we know what is this in cohomological terms. In cohomological terms, this is just the second cohomology of the Galois group, G, well, say K separable over K of the roots of unity. Yeah, so these are roots of unity and zeta in K, such that zeta to the R is 1. Yeah. Yeah. This is from Kummer exact sequence, that has such an identification. Yeah. So the claim is that there is a natural. Yeah. Maybe before going further, let's define. Oh, I'm sorry. There will be another K, which is just which comes from K groups. Yeah. So there will be K of K. It's a bit complicated. So, but maybe we should change. Well, let F be a field. Then K dot of F is just well, it is a direct sum of K i's, so from 0 to infinity, K I m of F. And by definition, this is just the quotient of the tensor algebra. Well, actually, the only case we need is just K2. Yeah, maybe. Well, this is just the tensor algebra. This is the quotient of the tensor algebra of the multiplicative group of F. By the two-sided ideal. So this is a two-sided ideal. Generated by the following elements: A tensor 1 minus a for all a in f star minus 1. Yeah, minus 1 because 1 minus 1 is not invertible. Yeah, so actually what we need, we will need only K2. Yeah, so what is this? This is just, well, this is, K, so K0 is just Z, so examples, so K0 is, of any field is just Z, and K1 of F is just the multiplicative group, and we will be interested only in K2. This will be just F tensor square of F of the multiplicative group modulo the subgroup generated by these elements. So A is here, and this is just the Z module, the abelian subgroup generated by these tensors. Yeah, well, and you can check that. What can you say about this group? Well, that it is almost until, well, the elements here, so the classes here classes, so the class of A tensor B is denoted by such brackets. Yeah, so this is just the class. You see, if you have decomposable tensor here, A tensor B, when you consider it as its class modulo this relation in K2, then it is denoted by this way. So, of course, this symbol is additive in each variable here, on the left and on the right. And what else can you see? It is almost antisymmetric in the following sense. Well, for instance, you cannot say that a symbol of A and A is 0. No, but you can say that the symbol of A and minus A is something like that, because you see that you can change Yeah, maybe let's start with anti-commutative. Well, it's called graded commutative. This ring is graded commutative in the following sense that let's anyway, yeah, we anyway need this. Let's start with the following identity. So this will be we start instead of A, we write inverse of A. Yeah, the inverse of A, and the 1 minus inverse of A is written as 1 minus A over minus A. Yeah, this is just 1 minus 1 over A. Yeah, so this is 0. Now this is minus. Well, you see that we can invert this A. This will be just minus. Well, let's write this. Minus A, 1 minus A, minus A. Yeah. And now you see that a symbol of A and 1 minus A is 0. Yeah. So we can remove this. This will be minus A minus 1 over minus A. And now we invert this and change the sign to plus. So this is A minus A. Yeah? So it is not completely antisymmetric, but some kind of. Yeah. And now what else? But it is antisymmetric in the following sense. So if we start with the following equation, we already know that symbol of A and the minus A is 0. So we can write AB now instead of A minus AB. And well, of course, here we assume that a is not 1, yeah. But well, it's not a big deal because when a is 1, then it's already 0 for trivial reasons. So a is not 1. Well, and here we know that this is 0. This is always 0. This is always 0. The only, yeah. So here a and b just in f star. Yeah. So this is 0. This will we use additivity here. So this will be symbol of a minus ab plus b minus ab. Now we know that the symbol of a minus a is 0. So this will be symbol of a and b. And we know that symbol of b and minus b is 0. So this will be b a. And so you see that it is antisymmetric in this weak sense. Yeah. So we don't say that a and a symbol of a and a is 0, but we know this and this. Yeah. Okay. So all right. Now what else? What else? Yeah. Now we can assume, so far we didn't. This is general definition, yeah, and just one remark, some obvious remark. Obvious remark is that about K1. K1 is just the multiplicative group, and we may ask what is K1 modulo R. Yeah, we don't need R. Just a second. Yeah, let's assume that it is. Yeah, assume that characteristic doesn't divide R. Characteristic of F does not divide R, and then we can write. So here we assume that let's yeah, maybe we can put here a bar, yeah. Yeah, so we can write the following exact sequence. So mu R. So this is the set of inseparable closure. Separable closure, and this is raised to the rth power. Separable star 1. And then what can we see? We see that F star, so we pass to the cohomology, so take Galois invariance and the derived functor, that is cohomology. And we get, here we get, so we take invariance, here we get just F. This is raised to the rth power, F. Then H1 of the, well, this is G, of the Galois cohomology of mu R, of the roots of unity. And then by Hilbert 90, this will be 0. So the first cohomology of the multiplicative group will be 0. Yeah, so this means that, sorry, star. This means that the first cohomology, that F star modulo nth powers, I think we have already met this, no, not yet? Well, doesn't matter. But now we really met this. Yeah, so mu R. Yeah. Okay, so well, and this is you can think of f star as k1. Yeah, so this is k1 modulo n, k1 of f modulo n. And actually, it turns out that well, and of course, and we haven't discussed this, but there is a multiplication cohomology. So it's I don't really want to say much about the multiplication because it's quite a bit technical, so it takes some efforts to deal with. But the idea is that that there is a multiplication, so if you have arbitrary group G, you have one module, and you have another module, then there is a multiplication which is a map, some natural map from G from this another group, and to say M tensor. Yep. And so in particular here you have if M and the N are just roots of unity, and I and J are 1, then you get a map from the tensor square of G mu R tensor square to instead of tensor square you can take any power, say n. Then this will be a map to nth cohomology. Well, of course we don't go further than 2. Well, let's write 2. Let's write 2. So this will be the map to the second cohomology of G of mu R tensor square. Yeah. So what can you see here? You see that this is just the tensor square of f. This is the tensor square of f modulo R. Yeah. So modulo subgroup generated by R multiples of elements of this subgroup. And this is more or less, so if we assume that this field contains a primitive root of unity, if a field contains, so if f contains an rth primitive root of unity, then this mu R is just Z model. Yeah, because so this tensor square is just more or less the same. Okay? And let's call it zeta. And then the point is that there is a natural map, namely. So what we are going to do is just to define concrete central simple algebra. So namely, just a second. Yeah. So let's define the following. Algebra that we denote it by A zeta A alpha beta. So what is so zeta is just a primitive root of unity. Alpha beta are elements of K star, and it is generated by elements. So is a K algebra, maybe is the K algebra. Well, of course, we assume that it's associative. Yeah? associative unital okay, algebra generated by x and y, generated by two elements, generated by x and y, and with the following relations: x to the r is alpha, y to the r is beta, and yx is zeta xy. Yeah. So now the exercise to check that this first of all, so it is a central simple K algebra. And then well, let's call it just A. A is a central simple K algebra. Central simple K algebra. Yeah. Next, its dimension over K is r squared. And there is a canonical homomorphism, which is actually an isomorphism, but we don't touch this. And there is a canonical homomorphism. There is a canonical. This has nothing to do with this concrete A, because this will be, but it uses in the proof canonical isomorphism. The following one. So we take more or less K2 of K modulo R, but we slightly modify to this to make everything canonical. We take homomorphisms from mu R and then map it to the Brouwer group of K, actually to the R torsion. Yeah, and this works as follows. So you take maybe let Xi be an arbitrary element. Yeah, so we starting from this element, we have to construct certain algebra here. Let's so we have to so we send so suppose that we have phi here. We send it to what? Well, it's a bit complicated because we have to consider only those elements. Yeah. So suppose that phi is not arbitrary, but only such that it sends Xi to alpha beta to the symbol well, of course modulo R. Yeah. R. And then we send phi to, well, you can imagine where, but of course it's not evident that everything is well defined. Just send to A psi alpha beta. So it's not over, but we'll see that it's not that big deal to. Yeah. So let's start. First of all, why it is a central simple K algebra? Well, first of all, its dimension. What is its dimension? Is it evident that it is R squared? Yeah, that's right. Yeah. So you see that it is generated by monomials x, y, y. You see that if we have, in principle, this is generated by monomials like x to y, I1, y j1, x I2, y j2, and so on. But using this relation, we can move all y's to the right. Yeah. So now we have only these monomials, and here I and j, and of course here I is can be made strictly less than r, and the same for j. Yeah. So that's how we get, and there are, of course, there are no more relations. Yeah, that's it. So its dimension is clear. Now, why is it? So two questions: why it is central? What is simple? What is in the center of this algebra? So in principle, there could be some element like this. Yeah. Alpha is not good. Gamma. So, if this is a central element, what are these coefficients? Central. So, for instance, if zeta were 1, yeah, then of course this algebra was commutative, yeah. So central is the whole algebra itself, yeah. So it's yeah. So what can we do? Well, of course there is no much options, yeah. We just have to look at commutator, yeah. Or just so what is x gamma? What is gamma x? What is x gamma? It is over the same range of indices, yeah? A, I, j, and then Что? Что снизу? Yeah, so yeah, that's right. So when we multiply by x on the right, then we get zeta to the j, yeah, to the j, xi plus 1, g, yeah, and here just xi plus 1, y, j. And of course there are no, these monomials also form a basis, yeah, because we just get rid of pure powers of y, yeah, and then instead of powers of y we have now rth power of x times this powers of y, yeah, so these are the same. Rth power of y is just alpha, yeah, alpha times this. Yeah, so this is also a basis, and therefore, so the conclusion is that Aij is equal to 0 unless what? Unless j is 0. Yeah? Что, Саша, что-то вы так смотрите с удивлением?
У нас z это уже примитивный корень из единицы.
Примитивный.
Важно вторую степень ввести и получить единицу.
У нас нет этой степени. У нас G и ING are strictly smaller than R. Yeah? And the same trick with Y. Yeah? So that ij is 0 unless I is 0. Yeah. So this means that it is central. Yeah. Now, why is it simple? Okay, so yeah, so we maybe we can erase this. Simple. Why is it simple? Well, there are two options. I think there is either we can. How do you think? Well, you see that actually what we are doing is reminds me something. Yeah, something we have already done, namely. Namely what? Yes, but quaternions are more special. But I mean, you see, we have already dealt with certain class of algebras. Namely, you see that so assume that k. We don't have big K. Well, let L be a field. G certain automorphism group. Automorphism group of L, and we consider this and phi a two-cocycle on L with values in the multiplicative group of L. Phi a two-cocycle. And then we have defined such a ring, yeah? And we have already checked that this is a central simple algebra over, so this is a central simple algebra over the fixed field, central simple algebra over the fixed field of G. Yeah, so, and it seems that we more or less repeat the same argument, yeah? So maybe there is a way to identify these. So where is? Can you see some group here, some field, and so on? Can you see some group or field? So, well, of course, here is, well, of course, here is the group. The group is G. So G, oh, sorry, the group is the roots of unity, yeah? It's clear. Next, what is our fixed field? Our fixed field is K, yeah? So our, yeah, maybe one more. Well, but of course, there will be so we have to produce some extension, yeah, some cocycle. Can you see any cocycle here? Yeah, so for instance, we can think, well, we have what? We have, well, we can choose y or x, so yeah, so we can take just, of course, at least under certain assumptions, for instance, if alpha, if you see that, if, for instance, if alpha is not a perfect power, well, for instance, if r is prime and alpha is not a perfect rth power, yeah, then we can just add the rth root of alpha, yeah, something like this. So suppose that suppose that k of rth square root of alpha is of degree r, yeah? So this is, for instance, if we suppose this, then we can say that what is our, that our G is just generated by y. Sorry, it's not completely, yes, we can we write this? Can we write that? Can we assume that it's generated by y? Yeah, so that's our. We want. Yeah, so if we write this way, then we get exactly. Then we get exactly what we want, namely. How does y act on x? Exactly. It acts exactly by conjugation. Yeah, so it's. Yeah, so it's we can write that it is yes, this is precisely what we want. Yeah, so it's x by conjugation. This is kind of conjugation, and now conjugation means you see that if all if this extension is of degree r, then any automorphism acts on this and on this element just by multiplication by some power of zeta. Yeah. Now what? How did we define multiplication in this ring? It was defined as so G times H was G times H was phi of GH. GH, yeah? So, what do we want? We want, well, that's, so we define this as follows. We say that, and what is G and H? G and H are just powers of Y. So, we say that, so phi of y yj is just 1 if I plus j is less than r, yeah, and it is what? It is what? It is beta. It is beta. It is. So, what are the options for I plus j? It may be less than r. It may be. It may be. It may be greater than or equal 1. Maybe. And anyway, it is less than 2r. Yeah, it is less than 2r. And therefore, here we put Q. Oh, sorry, beta. Beta, yeah, beta. Yeah. And one has to check that this is a cocycle. Yeah. Well, that's an exercise. But then, after you have checked this, we know that this is a central simple algebra. Yeah, well, of course, this is a little bit cheating because we assume that alpha is not a power dividing r. Yeah, so it's a bit cheating, but anyway, it's you can check that. Yeah, but now let's look at these constructions to make sure that it is. You see that we want some kind of homomorphism. Yeah. Sorry. Here I stated that it is canonical isomorphism, but we're definitely not. We're not going to prove this because it's a complicated theorem due to Merkuriev and Suslin. Merkuriev, Suslin. So we only can check that this is a homomorphism right now. Yeah, and for that, sorry. So far we didn't even check that these factors through the quotient like this. Yeah. So that's the question. Yeah. So first of all, we have to check that if beta is 1 minus alpha, then this algebra is trivial. 1 minus alpha. Yeah. So what is this? That's the question. So the claim is that this is a trivial algebra in the sense that it is matrix algebra. So can you construct an isomorphism? Well, actually, it's not that easy already. Yeah, so let's construct. Well, of course, you can do this more or less directly, but maybe it's easier to apply the following lemma. So we assume that A is a simple K-algebra, K-algebra of dimension R square, and X satisfies some polynomial relation, say f of x is 0 for some f which is a polynomial, and its degree is strictly less. Sorry, its degree is r. Its degree is r, but it is maybe the minimal polynomial. So fx is such that its minimal polynomial is of degree and f is the minimal polynomial. Yeah. Okay. And the claim is that yes, if f is if f is a product of distinct linear factors, then the algebra is matrix. Then A is isomorphic to matrix algebra over K. Yeah. So yeah. Okay, yeah, so this kind of evident, yeah, namely we can just generate the algebra, subalgebra by x, yeah, so that so this algebra is, this is a minimal polynomial, so it's we can consider f of t, yeah. So this is an embedding. This is an embedding into A, namely we send t to x, and what else? And on the other hand, this is just the direct sum. You see that it's a product of distinct linear factors, yeah. So it's this means that it is just a direct sum of r copies of K. Yeah? Well, then take projectors. Yeah, so we have projectors. And this EI just projector onto onto the ith summand. Yeah. And yeah, and then just take some. Okay, yeah, so we have, yeah, so we can split this algebra into the sum of left ideals. I, so take all these projectors, and then we just embed this A. So we can embed A into endomorphism. Well, say fix some. Yeah. So. Well, as usual, you see that what we do in such cases, we just embed the ring into the endomorphism ring of the module, in our case, of an ideal, into So we take some I. Yeah, so we take some I. We will see which one, and take endomorphisms of this module of this ideal, where D is just the endomorphism ring of this left ideal. Yeah, endomorphism as left A module. Yeah, and our ring is simple. So we just have to, okay. Yeah, so maybe we have to choose. Sorry, you see that here we have such a, we know that A is R² dimensional. So we have such a decomposition. So we may assume that dimension of so we choose such I that dimension of this dimension over K of this ideal is at most R. Yeah, so all dimensions cannot be strictly greater than R because the total dimensions are squared. Yeah. Now what is this endomorphism ring? This endomorphism ring, well, of course, it is it's kind of you see that the endomorphism ring of the whole A is just the opposite of A. Yeah. So and here we consider only those elements that preserve this left ideal. Yeah, so it means that this endomorphism ring is embedded into the opposite of A. Yeah, and yeah. Okay, now. What else can be said? Yeah, and also you see that here we, of course, K is in this because it is in the center. So, and on the other hand, we you see that here we look at endomorphisms over this algebra, and of course these endomorphisms are contained. And they are contained in the endomorphisms over K. Yeah. So endomorphisms over K of A, E, I. So actually we don't really use this. Yeah. Well, I mean, it is important. Well, it is important in the sense to make sense of this inclusion. Well, but we don't really use this. Yeah. So now look at this. So this is inclusion, maybe a non-strict one. Yeah. So now look at this space. Yeah. So this space, this is at most r-dimensional over K. So the dimension of this algebra is at most r squared. Yeah. So dimension over K of this endomorphism algebra is at most r squared. But you see that A is simple, so this homomorphism is injective. So this homomorphism is injective. A is r squared dimensional. Yeah, and it is embedded into something r squared dimensional. So it is actually inequality. Yeah, so they are canonically isomorphic. They are canonically isomorphic, and this is just the matrix algebra. Yeah, so that's it. So it's okay, and now we can prove that something. Yeah, we can prove something. Namely, okay. Yeah, we are coming back to this x and y. We have to So we need some. Yeah, we have to check something. Namely, so let's. So we're going to raise x plus y to a certain power, and look what's going on. So what's this? When we raise x plus 1 to a certain power, we get certain linear combinations of monomials. Yeah. So let's denote this linear combination as pi I n and sum from 0 to n. You see that in principle, we just you see that we just get rid of brackets and look and just move. We don't use relations x to the r is alpha and y to the r is beta. We just use this commutation relations. So there will be n plus 1 summons with certain coefficients that we denote pi I of zeta and just x to the I, y, and minus I. Yeah. But now, actually, in fact, this is very PIN is just a polynomial. Yeah, it's just a polynomial. So this one. So and then this is a polynomial evaluated zeta. Yeah, so it's not just a notation, but certain concrete thing. Namely, let me write this down. So this will be polynomial with integral coefficients, it will be the product. So it is written as a rational function, but it turns out that it is in fact a polynomial. So it is product of 1 to I, 1 minus t n minus s plus 1 over the product in the same range from 1 to I, 1 minus t to the s. Okay, so let's see whether this is indeed a polynomial. Maybe it's not. Yeah, so maybe it's just yeah. Yeah, let's see. So first of all, is it a polynomial? Yeah, it's kind of binomial coefficients. Yeah, so it's kind of binomial coefficients. Да? Yeah. Ну а что геометрическая прогрессия? Ну, это вы имеете в виду в предел, да, в единицу? Предел, когда t к единице стремится. Или что? Да, это в смысле, что это t биномиальный коэффициент. Да. Угу. Да-да. А почему это многочлен? Это многочлен? Или нет? Ну, смотрите. Yeah, for instance, if I is 1, then it's okay, yeah? If, yeah, actually, the argument is more or less the same as for, you see, the argument is the same as for binomial coefficients, because, so, can you explain that binomial coefficients are integral? Without interpreting them as binomial coefficients. I mean, just quotient some factorials, yeah. So this is, well, this is an exercise, yeah. Or just by, well, maybe by induction. By induction, because yes, because for binomial coefficients you have certain relation, yeah. You know this Pascal triangle and so on. And here you also have such kind of a Pascal triangle. Yeah. So. Okay. And the claim, yeah. So the idea is that you prove this by induction. By induction and. Okay, so what happens if n is R? If n is R, then what happens here? If n is R, then this is 1, yeah? So pi r of zeta. So you see that if we put here zeta, then n disappears. Here we get 1 minus s, but this is just a permutation of these roots of unit. Yeah, so this is 1. But no, sorry, excuse me, it's not 1, it is 0. It is sorry. Wait. It's not good because yes, it is 0. It is 0, except we have to be careful. Namely, yeah, we have to consider cases. Yeah, so first case is I is 0. If I is 0, then this is 1. Yeah, this empty. So this is 1. This. If I is 0, this is always 1. P not n is 1. Yeah, this is. So this is so if I is 0. Next, if I is R. If I is R, then if I is R, then it's a bit complicated. Yeah, so we have to check this. Maybe if I is R, we have to calculate this. And if I is between 0 and R minus 1, then this is 0. Yeah, because downstairs we have something non-zero. Yes. This doesn't. The denominator doesn't vanish. But numerator vanish when s is 1. Then we get 0. Yeah, so this is 0. Otherwise, and we just have to check what is this coefficient. But it's not. It is easy just because if this is the power of x. Yeah, and the power of x, we know what is that. This is just 1. Yeah. We just get rid of brackets, so we get x to the n. Yeah. So the conclusion is that x plus y to the r is x to the r plus y to the r, and this is alpha plus beta. Yeah. Okay. Yeah. So now what can we see? So if alpha plus beta is 1, then x plus y satisfies lemma. Is lemma. Yeah, so we get something to the, because we have all roots of unity, yeah, all our roots of unity, and they're distinct. So we get decomposition into linear factors, and therefore this algebra is trivial. Okay. Well, of course, when this is well, of course, alpha is not 1. Alpha is 1 is invertible, but but not 1. Otherwise, it's meaningless. Yeah, we haven't defined this when something is 0. Okay. Well, of course, we haven't. So we checked this Milnor-Sternberg. This is called Sternberg relation. But of course, we have not done many things. Yeah, we have not done. Well, maybe you should check that this algebra is simple. I mean, honestly, yeah. So far, you see, we have not checked that it is simple. We just said that if alpha is not, if alpha defines, if adding rth root of alpha defines an extension of degree r, then indeed it is simple. But we haven't checked this directly. Yeah? So that's an exercise you could do by yourself. Yeah. So yeah, and this is first thing that we did not check. Next here, so far we haven't constructed even a homomorphism because we have to check that we have to check that, well, of course, yeah, you may ask, well, of course, we can just, define, we can fix, you see that this group is isomorphic to just K2 of K over modulo R, yeah? So because we can fix some zeta as we did here. And then homomorphisms from this group is just, so this is given by zeta. Yeah, so this zeta, we just look at the value of this homomorphism on zeta. Yeah, and that gives us identification of this group. And then what can we do? Well, so far we have just a map from essentially a map from K star times K star. Yeah, so okay. So what we have to check that this map is, yeah, you see, we took alpha and beta, so element of the Cartesian product of two copies of K star, and constructed certain central simple algebra. But we have to check that it is this map is bilinear. Yeah. If we check that this map is bilinear, then we can conclude that it factors through this, and we already know that it vanishes on Steinberg. On this kind of pairs, yeah, and therefore, if we know that it is bilinear, then we can conclude that it factors through K2 of K. And of course, if as we know that it is Artosian, do we know this? Yes, because we know the dimension. Yes, dimension we know. So it is in Artosian, so it factors through this subgroup. Yeah, so to prove that, to construct this homomorphism, we only need to check the linearity. Yeah. And how about that? Or another option is, yeah, so we can just, to check the linearity. Yeah, to check the linearity, actually, yeah, so essentially what we can do, we can just construct, actually, I'm sorry, I think we have already, we more or less done this, yeah, more or less in the sense that somewhere here. Namely, we have constructed a certain cycle. So we constructed a map. So what we have already, well, not really, but more or less done. We have constructed a map to H square. What is beta? Ah, yeah, it's okay. So beta is I'm sorry, maybe it's not that good because yeah, maybe it's not that good because because no, is it okay? Or not really. Yeah, maybe the good question is whether is this a cocycle? Is this a cocycle? Why not? Yeah, why not? Because, yeah, so the cocycle simply means that this is an associative algebra, yeah? And it is. It is an associative. It is it? It is, of course, yeah? Because by definition, our algebra is associative, yeah? And this is just the... We just have rewritten this algebra, yeah? So it's... we just write that yeah, just a second. If yeah, so I plus j is it may be yeah. So if it is between r and to r, then we just yeah, it's okay. It's okay. Yeah. So it's a cocycle. A cocycle. Yeah, so then this means that we have constructed a two cocycle yes, but then of course what happens? Yeah, so you see that this cocycle is multiplicative in beta. Yeah, so if we have beta and beta prime, then the product goes to the product of the cocycle of the cocycles. Yeah, so it is indeed multiplicative. Не согласна. Повторить? А? Yeah. So what do we have to check? We have to check that here we have alpha, a pair of alpha, beta prime, and we have a map to, well, certain cohomology, well, maybe some L star, yeah, some extension, and this is some Galois extension, and this is a Galois group of this extension. So we have to check that such a pair has the same image as the image of alpha beta plus the image of alpha beta prime. Yeah, in the well, the classes. Yes. We want to check that this map is bilinear. Yeah, so for instance, if we fix alpha, then it is linear in beta. And what is our map? Our map sends alpha beta to the cocycle, to the following cocycle. So we don't, alpha is fixed, and our L is just in our, well, here is our L. Yeah, and our cocycle is written here. So y powers of y are, correspond to the Galois group. So we have identified our Galois group with as this set. Yeah, as this set. Yeah, so. Yeah, so we say that our cocycle is given by this way, yeah. And if we take instead of beta, take beta prime, then we get exactly the product of these cocycles. Product means sum, as our group law here is written multiplicatively, so it is called product. Yeah. Yeah. So we have checked linearity in, well, more or less, because we have to. You see that we have to be careful. Well, we have to be careful. Namely, we choose alpha, which is not rth power, yeah, and then we prove linearity in beta, and then we choose beta, which is not power of rth, well, not rth, but all divisors of, yeah, it's not dth power for any d divided in r, yeah, so it's, ну, понимаете, да, там, в общем. Yeah, so I mean, it's you have. There are much more words to say than I have already said. Yeah. But after that, you see that it is indeed bilinear, and then as it is bilinear, and it vanishes on this relation. So it factors through K2, and it factors through K2. Of course, it's R-torsion, so it factors through the R multiples of the elements of K2. Yeah. Yeah. So. Yeah, maybe, well, and yeah, so we have such a map, and but of course, to prove that this is an this is an isomorphism, it's not very easy. Yeah, so it's, well, you can write this paper by Purifans, you know. Вот. Так что, наверное. Ну, не знаю, пока что. Yeah, maybe we should stop with the Brouwer group. Maybe, if you don't have any ideas. Если есть какие-нибудь, if you don't have any suggestions about Brouwer group. Или что-нибудь еще надо сказать про группу Бrouwer. Значит, ну, you see that there are several directions. Namely, so far we only dealt with local fields like periodic or something like this. But of course, you can ask, what about number fields? And but I mean, it's a little bit. Well, we can discuss this, but it's a more specific direction. Yeah. So if you don't have any particular interest, then maybe. Что скажете, нет? Или? Ну, то есть не сейчас, это как бы так на будущее имею в виду. Ну, смотрите, если есть какие-нибудь соображения, вы их высказываете, потому что сейчас такой момент, когда мы переходим к чему-то. Yeah, so actually the only thing we can do in more or less in the same spirit, but in more abstract and more, well, it's a very short topic, it's Morita equivalence. So Morita equivalence. Here, you see, when we deal with Brouwer group, what is a Brouwer group? It's certain equivalence it's a group of classes consisting of equivalence. This is a set of equivalence classes, yeah, of where we say that two algebras are similar if I don't remember what, yeah, so somehow, yeah, but you can say that if they are Merit equivalent, yeah, for instance, Merit equivalent means that their categories of left modules are equivalent. So we may discuss next time Merit equivalence in general context. Here we only dealt with the central simple finite dimensional algebras, not we can take a look at just arbitrary rings and see some examples. They are equivalent. Oh, and so, actually a description of Merit equivalent rings. Yeah, but вот, ну, я не знаю, что. Все, будем считать, что с группой Брауэра покончено. Но только вы это сами все-таки упражнения. Разберитесь, мы же тут много чего не говорили. Вот, ну, так просто, чтобы нет ощущения, что обманывают. Ну что? Что-нибудь успели?